Hello, and welcome to the Sleepy Curiosity channel. As you find a comfortable position, let your body begin to release the weight of the day. If this quiet journey is already starting to slow your thoughts, consider subscribing now, so these stories can keep finding you night after night. And now, let the relaxation settle into your breathing. You're not made of stardust. You're made of dead stars. There's a difference. Dust is what's left over. A dead star is what exploded, scattered its core across space, and rebuilt the universe around it. And those fragments are in your blood right now. And the more we look, the more remarkable that becomes. It all began with silence. Not the silence of an empty room, not the silence of a quiet night in the countryside, not the silence you find when the sounds around you fade and the mind begins to slow down. This was a different kind of silence entirely, the dense, warm silence of the universe's earliest moments, when there were no stars yet, no structured light, no recognizable form of anything. Just hydrogen and helium slowly spreading through newborn space, gradually cooling, obeying the one force that has always been present since the very beginning, gravity. And that's how everything began to organize itself. Unhurried. Without declared intention. With no one to observe or record it. Immense clouds of gas, distributed almost uniformly through young space, began to yield to their own collective weight, folding inward in slow movements, imperceptible on any human timescale, but absolutely inevitable on scales that exceed any clock ever built. Where the gas grew a little denser, it grew denser still, because gravity calls more gravity, and matter calls more matter, and collapse feeds the very collapse it started, a process that, once begun, cannot be reversed. This shouldn't have resulted in something so beautiful. It should have resulted in chaos. And at first, it did result in chaos, but a chaos that contained within itself, hidden inside its own rules, the possibility of a future order that would take billions of years to emerge. What makes this process so fascinating, and it's worth letting your mind rest on this idea for a moment, is that it didn't follow any clean or predictable sequence. It wasn't an orderly construction, brick by brick, with a blueprint and set measurements. It was a chaotic, turbulent process, full of collisions between clouds crashing into each other at speeds that seem absurd today, full of disruptions that sometimes destroyed what was forming before it could gain any coherence. And yet, from that immense chaos, from that swirling mass of gas and gravity that lasted hundreds of millions of years, there eventually emerged a galaxy with spiral arms of an elegance that seems almost deliberate. Order emerged from chaos. Not in spite of the chaos. Through it. And that realization, that the elegance of galactic structure doesn't contradict the turbulence of the process that created it, but is in fact its direct consequence, is something worth letting the mind rest on, while the body continues sinking into its own quiet weight. There's a detail that changes everything in this origin story, and it's a detail that took decades to be fully appreciated by astronomy. The matter we can see is stars, gas, dust, everything that emits or reflects some form of radiation, wasn't what organized the galaxy first. Before any star ignited, before any cloud collapsed into a protosun, before any visible structure took shape, there was another structure already present in space. A web of matter that emits no light, reflects no light, interacts with electromagnetic radiation in no known way, but that has mass, and therefore curves space-time around it, and was therefore already shaping the cosmos in ways that visible matter simply followed. The Milky Way we see today, with all its beauty and complexity, is in a certain sense the shadow of a structure we can't directly see. That idea deserves a moment of genuine stillness. All the beauty of the galaxy, all the spiral arms with their star-forming regions, all the colorful nebulae lit up by young, hot stars, all the stars shining in the sky of some planet somewhere in this 100,000 light-year structure, is just the visible fraction of something much larger. The skeleton of the galaxy is invisible, and it's the one that holds and organizes everything we can observe. The Milky Way is approximately 13.6 billion years old. The universe is 13.8 billion. The difference between those two ages is so small, in cosmic terms, that we can say without much exaggeration that the galaxy is almost as old as space-time itself. It began forming just a few 100 million years after the Big Bang, when the universe was still too young to have produced any element beyond hydrogen, helium, and trace amounts of lithium. Think about what that means for a moment. 13.6 billion years. A number so large it loses meaning the moment we try to picture it. If each year were represented by 1 second of time, 13.6 billion years would be more than 430 years of consecutive seconds, more than 4 centuries of a clock ticking without stopping, second after second, just to represent the age of the galaxy. And yet, on that absurd timescale, the entire history of humanity, from the first signs of culture, tools, language, would take up less than a minute on that same clock. Everything we know of civilization, of history, of art, of science, of all the accumulated knowledge of every human being who ever lived, on a galactic scale, it happened in the blink of an eye. What almost no one realizes is that this doesn't diminish the importance of what happened in that blink of an eye. It only resizes the stage on which it happened. The first stars that ignited inside the Milky Way were made exclusively of primordial hydrogen and helium. No carbon, no oxygen, no iron. None of the elements we consider essential for life, for rocky planets, for anything that resembles the world we know. They were stars of a chemical simplicity that no longer exists anywhere in the observable universe, because the generations of stars that came after them enriched the cosmos in ways that can't be undone. And those first stars, precisely because they were made of such light materials, were enormous. Tens, hundreds of times more massive than the Sun. Because in the absence of heavy elements to efficiently dissipate heat, the cores of collapsing clouds kept accumulating mass until they reached sizes rarely achieved today. They were luminous giants that likely lit up the early universe with an intensity no current star can match. And because of that, they lived extraordinarily short lives. A few million years, not the billions that characterize stars like the Sun. And when they died, they didn't die quietly. They exploded with a violence proportional to their mass, dispersing through space the first heavy elements they had forged in their cores during the intense lives they had lived. Carbon, oxygen, nitrogen. The basic ingredients of life's chemistry, scattered through the primitive interstellar medium by the deaths of the first stars, mixing with the still dominant hydrogen and helium, enriching the gas that would one day collapse into second-generation stars, stars that would be born already containing those elements. None of those early stars are visible today. They existed, produced the elements that make up everything around us, and disappeared more than 13 billion years ago. But their legacy is in every carbon atom, in every DNA molecule of every living being that has ever existed on Earth. The first stars died so that we could exist. Not as a poetic metaphor, as a literal and precise causal sequence. This starts to get more interesting when we try to imagine what it would have been like to observe that early universe from the outside, if that were possible. A young galaxy, before the first supernova explosions had enriched the gas, would have been a structure dominated by intensely bright blue and white stars, a spectacle completely different from the mix of colors the current Milky Way presents. Red from coal dwarf stars, yellow from solar-type stars, white and blue from the hotter, younger ones. The young universe was much bluer, much hotter, much more violent, and much simpler. Complexity came with time. With each generation of stars that lived and died, the interstellar medium grew a little richer in heavy elements. With each supernova that dispersed its nuclear fusion products into space, the gas that would fuel the next generation of stars became a little more chemically varied. And with that growing chemical variety came possibilities the early universe didn't have: rocky planets, complex organic molecules, liquid water, and eventually, the possibility of structures organized enough to ask where they came from. Complexity is an emergent property of time. The formation of the Milky Way was not an isolated process. From its earliest stages, the galaxy has been incorporating smaller surrounding structures, dwarf galaxies that came too close and were captured by gravity, their stars gradually stripped away and distributed across the galactic halo over billions of years. This process has a precise technical name, hierarchical accretion, but the image it evokes is more direct and stranger at the same time. The Milky Way grew by absorbing other galaxies. Not violently and instantly, like two rocks smashing into each other, but slowly and gravitationally, like a whirlpool that gradually draws in everything that comes close enough to be captured. The smaller surrounding galaxies entered the Milky Way's gravitational field, were stretched by tidal forces, had their stars gradually pulled away in streams that elongated along their orbits, and eventually lost all independent structural identity. Their stellar populations quietly dissolved into the halo of the larger galaxy. The evidence of this process is written in the galactic halo to this day. Streams of stars with slightly different chemical compositions from those in the disk, stretched traces of galaxies that ceased to exist as independent structures billions of years ago, their stellar populations now silently incorporated into the galaxy that absorbed them. The Sagittarius stream is one of the clearest examples, an arc of stars wrapping around the Milky Way in multiple rings, a remnant of a dwarf galaxy that hasn't been completely absorbed yet. What makes this particularly unsettling and fascinating at the same time is that this process is still happening today. The Sagittarius dwarf galaxy is being absorbed right now. And the Magellanic Clouds, visible to the naked eye in the southern hemisphere as distinct nebulous patches separate from the galactic band, are being pulled toward the Milky Way and, at some still distant point in the future, should be completely incorporated. The Milky Way is growing right now. Silently, on timescales that exceed any human perception, but growing. In 2018, data from the Gaia satellite, an instrument of the European Space Agency designed specifically to map the positions and movements of stars with unprecedented precision, revealed something that rewrote the history of the Milky Way in a dramatic and definitive way. By analyzing the orbits and chemical compositions of thousands of stars in the galactic halo, astronomers identified a distinct population of stars that clearly didn't originate in the Milky Way. They came from a dwarf galaxy that collided with ours in an enormous merger, which occurred between 8 and 11 billion years ago. This event was named Gaia Enceladus, and it's considered the most significant merger in the history of the Milky Way. The collision was so intense that it deeply disrupted the structure of the early galactic disk, sending billions of stars into highly eccentric orbits that can still be traced in the halo today. And there are indications that this merger also triggered an intense phase of star formation in the galaxy's bulge, the compression of the interstellar gas caused by the impact setting off the collapse of clouds and the birth of billions of new stars. Part of the Milky Way's current structure was shaped by a collision that happened before the Sun even existed. That idea has an additional layer worth exploring slowly. The Sun is 4.6 billion years old. The collision with Gaia Enceladus occurred 8 to 11 billion years ago. That means that when the Sun was born, the galaxy had already recovered from the most significant merger in its history, had already absorbed the intruder galaxy's stars, had already reorganized its disrupted disk, had already passed through the intense star formation phase triggered by the impact. The Sun was born into a galaxy that already had a long history of collisions, absorptions, and reorganizations behind it. A mature galaxy, not a young one. There's a detail that changes everything about how we think of the galactic disk. When clouds of gas collapsed, any rotation they had was amplified as the material contracted, the same way a figure skater spins faster when she pulls her arms in toward her body. Gas moving perpendicular to the rotation axis was gradually dissipated by collisions between particles, while the circular motion was preserved through conservation of angular momentum. The result was a progressive flattening of the structure into a thin disk. Physics didn't choose the spiral shape. Physics simply obeyed its own rules, and the shape emerged as the inevitable consequence of those rules operating over billions of years. The oldest stars, formed before that flattening was complete, have much more inclined and eccentric orbits. They belong to what's called the stellar halo, and their roughly spherical distribution reflects the more chaotic and less organized state of the galaxy in its first few billion years. They're dynamic fossils. Their trajectories hold the memory of how the galaxy moved before it took on its current form. And the spiral arms, which seem like the most distinctive feature of the Milky Way when seen from outside, have a nature that completely contradicts their appearance. They are not fixed structures of stars. Individual stars move in and out of the arms along their orbits around the galactic center, like cars passing through a traffic jam on a highway. The jam exists as a structure independently of which specific cars happen to be in it at any given moment. What the arms represent are density waves, regions where gas and stars are temporarily compressed as they pass through, where pressure increases, where the collapse of clouds is triggered. And that's why star-forming regions are concentrated in the arms. Not because the arms are structures especially rich in old stars, but because the gas passing through them is compressed enough to collapse into new stars. The brightness of the spiral arms is the brightness of the continuous birth of young, hot stars that have just formed in those compression zones. Each spiral arm is a stellar factory in motion, not a static structure. And this is where things get strange in a very specific way. The Sun is not in a main spiral arm. It's in a smaller branch called the Orion arm or local arm, a spur between two more substantial arms known as the Sagittarius arm and the Perseus arm. Our position in the galaxy is not central, not in one of its most active or visually dominant structures. And maybe that's precisely what matters. The main spiral arms are much more violent environments. The density of star formation is higher, which means a higher density of supernovae, massive stars being born and dying in explosions that release amounts of energy capable of disrupting nearby planetary systems. Radiation is more intense. Gravitational disruptions are more frequent. A planet located in a main arm would have a much harder time maintaining stable environmental conditions for billions of consecutive years. Complex life, the kind that requires prolonged stability to develop from simple forms, prefers calm environments. And the Orion arm, with its lower density of star formation and its intermediate position between two more active arms, is a comparatively peaceful environment. The apparently middling and unremarkable position of the Sun in the galaxy may be one of the precise reasons why there's something here capable of observing and questioning that position. Around the Sun, in a bubble roughly 300 light-years in diameter, the interstellar space is unusually empty compared to the typical environment of the galactic disk. This region, called the local bubble, was likely sculpted by a series of supernova explosions that occurred over the past few tens of millions of years, which pushed the dense gas out of the neighborhood and left a low-density environment, a cosmic air chamber, around the solar system. The Sun is inside a bubble, inside a secondary arm, inside a spiral disk, inside a halo of dark matter, inside a group of galaxies, inside a supercluster. Structures nested within structures, at scales that grow at each level by factors of hundreds or thousands. And somewhere inside the smallest of those structures, a planet, and on it, you, resting while this story unfolds around you. For a long time, the center of the Milky Way was a region completely inaccessible to direct observation. The interstellar dust that accumulates over the 26,000 light-years between the Sun and the galactic center absorbs visible light with extraordinary efficiency. The original light would need to be 1 trillion times more intense to pass through that veil and reach us in visible wavelengths. The galactic center has never been and never will be directly observed by any conventional optical telescope. Think about what that means historically. Throughout the entire existence of the human species, through all the millennia, our ancestors looked up at the sky, developed mythologies about the stars, built calendars based on celestial movements, navigated oceans using constellations as maps. The nucleus of the galaxy itself was completely hidden behind a curtain of dust. There was no way of knowing what was there. No way to even suspect the scale of what was concealed. The existence of the central supermassive black hole, of all the stellar density of the bulge, of the galactic bar that crosses the center and from which the spiral arms originate, all of it remained completely invisible until the development of telescopes capable of operating at wavelengths that dust cannot block. Radio, infrared, X-rays, gamma rays. Each of those windows of the electromagnetic spectrum revealing different aspects of a region that has existed since the galaxy itself existed, but that remained completely hidden from the only species capable of building instruments to observe it. Sagittarius A star, the supermassive black hole occupying the dynamic center of the Milky Way, has a mass of approximately 4 million solar masses, compressed into a region smaller than the solar system. Imagine for a moment what that means. For millions suns, in a volume comparable to the space Neptune traces in its orbit. The density there is of a nature that known physics can barely describe. And yet, compared to the active galactic nuclei of other galaxies, Sagittarius A star is surprisingly quiet. Galaxies with quasars at their centers emit radiation that outshines the entire surrounding galaxy. The Milky Way central black hole emits only a tiny fraction of what would be expected for such a large mass with access to the surrounding gas. It's like an enormous engine running at idle. The capacity is there. The potential is there. But the scarcity of cold gas reaching the center, the geometry of the accretion flow, some mechanism we don't yet fully understand, keeps Sagittarius A* in a chronic state of relative quiet. The most direct evidence of its existence came from one of the most patient observational campaigns in the history of astronomy. For more than 2 decades, independent teams of researchers in Germany and the United States tracked the movement of dozens of stars near the galactic center, watching them year after year trace closed orbits around an invisible point. The star S2, for example, completes a full orbit in just 16 years, and at its closest point to the black hole reaches speeds of 7,650 kilometers per second, about 2.5% of the speed of light. Those orbits were observed in real human time, not inferred from snapshots. Followed year after year, with progressively more precise instruments, while the researchers who started the project grew older and trained new students who continued the work. And the orbit said everything that needed to be said. No object other than a black hole could concentrate for million solar masses into such a small space without collapsing into something even denser. The geometry was unambiguous. The black hole was real. That work earned Reinhold Genzel and Andrea Ghez the 2020 Nobel Prize in Physics, the leaders of the 2 independent teams that spent decades tracking those orbits. It was one of the most beautiful validations of long-term scientific patience that recent science history has produced. But it wasn't always so quiet down there at the center. There's compelling evidence that Sagittarius A* went through periods of much more intense activity in the relatively recent past. One of the most striking pieces of evidence is what's known as the Fermi bubbles, 2 enormous structures of hot gas extending above and below the galactic plane by about 25,000 light-years each, forming a total structure of 50,000 light-years in length. They were discovered in 2010 by the Fermi Space Telescope, and are clearly distinct from the surrounding environment in temperature, chemical composition, and high-energy radiation emission. 50,000 light-years. For reference, the entire galaxy is 100,000 light-years in diameter. The Fermi bubbles are structures that span half the length of the galaxy, extending perpendicular to the disk in both directions. These are not subtle structures. They're cosmic monuments to a past violence that we can still measure with precision today. The energy required to create these bubbles is astronomically greater than any individual stellar process can produce. The most widely accepted hypothesis is that they were generated by a period of intense activity from Sagittarius A*, or by an intense phase of star formation at the galactic center, occurring between 6 and 9 million years ago. The energy involved is equivalent to millions of simultaneous supernovae. 6 to 9 million years ago, our ancestors were already walking across Africa by then. The first representatives of the genus Australopithecus already existed, and the center of the Milky Way was in full eruption, emitting intense radiation in all directions, while those ancestors taking their first bipedal steps likely didn't yet have complex enough language to describe what they saw in the sky. The universe has its own events, on its own scales, completely independent of whatever audience may or may not be present to observe them. And there's something even more unsettling. About 3.5 million years ago, Sagittarius A star may have been bright enough to be classified as a low-luminosity quasar. This hypothesis is supported by observations of ionized gas in the Magellanic Clouds that appears to have been lit up by an intense pulse of ultraviolet radiation and X-rays coming from the galactic center at that time. 3.5 million years ago, the Australopithecines were already walking upright in Africa. The center of the Milky Way was in full activity, bathing the satellite galaxies with intense radiation, while our bipedal ancestors explored the savannas of a planet that, in that direction of the sky, was being crossed by energies that no accessible geological memory ever recorded. The satellite galaxies still carry the memory of that event in the form of ionized gas, like a frozen photograph of the radiation that struck them. The past doesn't disappear entirely. It gets written into the matter that survived it, waiting to be read by instruments sensitive enough to hear it. What almost no one realizes about the structure of the Milky Way is that it has a far more sophisticated architecture than a simple disk of stars. It has distinct components that play different roles in the galaxy's total dynamics, and understanding those components took decades of observation, partly because we're inside it, which makes getting an overall view extraordinarily difficult. The most visible component is the galactic disk, a flattened structure roughly 100,000 light-years in diameter and only about 1,000 light-years thick through most of its extent. If the Milky Way were scaled down to the size of a standard sheet of paper, its thickness would be comparable, or even less. It's an extraordinarily thin structure for its dimensions. Within the disk, there's an important distinction between two stellar populations that share the same space but have completely different histories. The thin disk, the denser central layer, contains relatively young stars with chemical compositions rich in heavy elements, and orbits that are nearly circular and well aligned with the galactic plane. The thick disk, just above and below, contains older stars with simpler compositions and slightly more inclined orbits. That division reflects distinct eras in the galaxy's history. The thick disk would have formed during a more turbulent period, when the galaxy was still being frequently disrupted by mergers. The thin disk, more organized, would have settled in afterward, when the galactic environment grew more stable. The Sun belongs to the thin disk, which places it among a population of relatively young and chemically rich stars, formed during a period of greater galactic calm. And at the center of the Milky Way exists a structure that doesn't appear in the spiral arms, the galactic bulge. A dense, roughly spherical region a few thousand light-years in diameter, concentrating a disproportionate number of old stars in a relatively small volume. For years it was believed the bulge was simply spherical. Infrared observations revealed that it actually has an elongated shape, like a peanut or a bar. That characteristic classifies the Milky Way as a barred spiral galaxy. The bar crosses the center, about 27,000 light-years long, made up predominantly of old, reddish stars. And the spiral arms originate from the ends of that bar, not directly from the center, but from the tips of the elongated central structure. The bar rotates too, but not the same way individual stars do. It has its own angular velocity, a pattern speed, and the region where that speed matches the orbital speed of stars in the disk is called co-rotation. This region has important implications for gas dynamics and where stars tend to accumulate or disperse over time. One interesting implication: the Sun is located near the co-rotation region of the galactic bar. Models suggest that this position contributes to the stability of the solar orbit over billions of years, avoiding orbital disruptions that would be more common at other positions in the disk. Again, the Sun's position seems to be privileged in ways we only understand in hindsight. Beyond the disk and the bulge, the Milky Way is wrapped in a much larger and much less dense structure, the galactic halo. A roughly spherical region extending hundreds of thousands of light-years beyond the visible disk's limits, containing mainly old and isolated stars, globular clusters, and diffuse gas at elevated temperatures. The halo's stars are some of the oldest in the universe. Their extremely simple chemical compositions, poor in heavy elements, reflect their origin in times when the universe hadn't yet enriched the interstellar medium with the products of successive supernovae. Their chemical fossils, preserving the signature of the early universe. One of those stars, known as Methuselah, was initially estimated at over 14 billion years old, which created an embarrassing paradox, since that would make it older than the universe itself. Later refinements in the measurements adjusted its age to around 13.7 billion years, within the acceptable range, but the episode showed just how technically delicate these estimates are and how large the uncertainties can be even with modern instruments. The halo also contains globular clusters, compact spheres of tens of thousands to millions of old stars, distributed mainly through the galactic halo. They're some of the oldest objects in the universe, many more than 12 billion years old. And the largest of them all, Omega Centauri, with around 10 million stars compressed into a region of just 150 light-years in diameter, is widely considered the surviving core of a dwarf galaxy that was devoured by the Milky Way billions of years ago. What was once an independent galaxy, with its own history, its own stars, its own internal dynamics, survives today only as a peculiarly dense cluster orbiting the halo of the galaxy that absorbed it. It's a form of partial and transformed survival, not what it once was, but still recognizable as having been something more. The halo also contains most of the dark matter associated with the Milky Way. Though invisible to any instrument, this component dominates the total mass of the galaxy. The total mass of the dark matter halo is estimated at around 1 to 2 trillion solar masses, between 5 and 10 times more than all the visible mass of the galaxy. That means the Milky Way we see, with its spiral arms, its stars, its nebulae, is only the smaller fraction of a much larger and completely invisible structure that surrounds and gravitationally sustains it. Without the dark matter halo, the stars in the outer regions of the disk would drift apart. The galaxy as we know it wouldn't exist. Dark matter is not simply ordinary matter that doesn't emit light. It's something genuinely different from anything the standard model of particle physics describes. It doesn't interact with electromagnetic radiation in any known way, it doesn't absorb, emit, or reflect anything. It's completely transparent to every form of light, at any wavelength. The only known interaction between dark matter and ordinary matter is gravitational. And that makes it extraordinarily difficult to detect. The only way to know it exists is to observe its gravitational effects on the matter we can see. The most direct evidence for the need for dark matter in the Milky Way comes from rotation curves. If all the galaxy's mass were made up of only visible matter, stars in the outer regions of the disk should orbit the center at progressively lower speeds with distance, the same way Pluto orbits the Sun much more slowly than Mercury does. But that's not what's observed. The orbital speeds of stars and gas across the galactic disk, beyond a certain distance from the center, stop decreasing and remain roughly constant, even in the outermost regions, where the density of visible matter drops dramatically. That behavior is completely inconsistent with the distribution of visible mass and requires the existence of an enormous amount of additional mass distributed beyond the disk, providing the extra gravity needed. The astronomer Vera Rubin documented this pattern systematically in the 70s, using observations of dozens of spiral galaxies. Her work was fundamental in establishing the dark matter hypothesis as a genuine physical necessity. And she never received the Nobel Prize for it before her death in 2016, one of the most discussed oversights in recent scientific history. The most studied dark matter candidate for decades was the WIMP, weakly interacting massive particle. The idea was that they could be detected when they occasionally collided with atomic nuclei in extremely sensitive detectors installed in underground laboratories. Despite decades of progressively more sophisticated experiments, no convincing direct detection has been made to this day. That doesn't eliminate the hypothesis. It only progressively narrows the parameter space. Dark matter may simply be of a different type than expected, with a much smaller mass, or even weaker interactions, or a nature completely different from any candidate currently being studied. There's also the axion hypothesis, a hypothetical particle of extremely low mass, originally proposed to resolve a completely different problem in particle physics. Over time, it was realized that axions could be viable dark matter candidates if they exist in large enough abundance. Unlike WIMPs, they have a peculiar property. In the presence of intense magnetic fields, they can convert into detectable photons. If axions are dark matter, they'd literally be permeating everything around us right now. Passing through walls, planets, stars, your body, without any perceptible interaction, an invisible ocean of ultralight particles that makes up most of the mass of the galaxy. It's one of the strangest and yet most seriously considered possibilities in contemporary physics. In the total energy budget of the universe, dark matter accounts for roughly 27% of the total content. Dark energy, a completely different form of energy associated with empty space itself, responsible for the accelerating expansion of the universe, accounts for about 68%. And all ordinary matter, stars, planets, gas, dust, galaxies, clusters, everything ever observed by any human instrument, represents only about 5%. The Milky Way, with all its scale and complexity and 13-billion-year history, is built from a very small fraction of the total content of the universe. What we call the visible cosmos is, in energy terms, a small minority of a larger reality we don't yet know how to fully describe. And yet, with that 5% of ordinary matter, the universe built stars, planets, complex organic molecules, and eventually beings capable of deducing the existence of the other 95%. This starts to get more interesting when we try to think about the space between the stars, what's called the interstellar medium. That space isn't empty. It's made up of gas in different physical states, dust of microscopic grains, and magnetic fields interwoven throughout the entire galactic disk. The density is extraordinarily low, in many regions less than 1 atom per cubic centimeter, but the scale is so enormous that the total mass represents a substantial fraction of the galaxy's visible mass. Hydrogen is the most abundant element in the interstellar medium, as it is in the universe in general, and it exists in 3 distinct forms that astronomers monitor separately. Neutral atomic hydrogen emits radiation at a very specific radio wavelength, 21 centimeters, that passes completely through interstellar dust and can be detected from anywhere in the galaxy. This emission was used to build the first maps of the gas distribution in the galactic disk, revealing the spiral arm structure with much greater clarity than any visible light observation could offer. Interstellar dust, which represents only about 1% of the interstellar medium's mass but has enormous astronomical effects, is made up of microscopic grains of silicates, amorphous carbon, graphite, and ice, with typical sizes of tenths of a micrometer. This dust absorbs and scatters the light from background stars, making them appear dimmer and redder than they actually are. For very distant stars in the galactic disk, the extinction can be so severe that they become completely invisible in visible light. But dust isn't just an obstacle to observation. Its cold surface acts as a chemical catalyst, allowing hydrogen atoms to combine into molecules much more efficiently than in free gas. Without interstellar dust, the formation of complex molecules in space would be much slower, and all the chemistry that precedes the formation of planets and eventually life would be profoundly different. Molecular clouds are the densest and coldest structures in the interstellar medium. Regions where the gas has reached densities and temperatures low enough for complex molecules to form and persist. They have temperatures of just 10 to 30 Kelvin, close to absolute zero, and they're the birthplaces of every star that exists in the galaxy today. Every star that has ever existed in the Milky Way, including the Sun, formed inside one of these clouds. And the interior of molecular clouds is a surprisingly rich chemical environment. More than 200 different molecules have been detected in the interstellar medium, including complex organic molecules like ethyl alcohol, formic acid, simple sugars, and even amino acids in meteorites that formed in similar environments. The chemistry of space is far richer and more complex than anyone imagined until just a few decades ago. The ingredients of life, or at least the ingredients of life's ingredients, are distributed through the galaxy's interstellar medium, produced by surface chemistry on dust grains, irradiated by nearby stars, mixed and redistributed by supernovae and stellar winds. Life may not be an anomaly that arose on an isolated planet against all odds. It may be the near-inevitable consequence of an interstellar chemistry that already spontaneously produces the basic building blocks needed. But we don't know. And that honesty, the acknowledgement that we don't know, is more valuable than any premature answer. The life cycle of gas in the interstellar medium is one of the most fundamental processes in galactic evolution. Diffuse gas condenses into molecular clouds, which collapse into stars. Stars process the gas through nuclear fusion, enriching it with heavy elements. When they die in slow stellar winds or supernova explosions, they return that enriched gas to the interstellar medium, from where it can be incorporated into a new generation of stars and planets. This cycle of progressive chemical enrichment is why the universe today contains far more heavy elements than it did at the beginning. The Big Bang produced almost exclusively hydrogen and helium. All the carbon, oxygen, nitrogen, iron, calcium, and other elements that make up planets and living beings were produced in stars and distributed through the interstellar medium over billions of years of successive stellar cycles. The atoms that make up any living being on Earth went through multiple such cycles before arriving here. The iron in the blood, the calcium in the bones, the oxygen in every breath, each of those atoms was forged inside a star that existed and died before the Sun was born. The interstellar medium of the Milky Way is not just the space between stars. It's the chemical laboratory where the ingredients of life were prepared over billions of years. When a massive star ends its life in a supernova explosion, it releases colossal energy, about 10 to the 44th power joules in just seconds, most of it in the form of neutrinos. The resulting shockwave expands through the interstellar medium at thousands of kilometers per second, compressing and heating the surrounding gas and creating an expanding structure called a supernova remnant. These remnants are visually spectacular. Filamentary and spherical structures glowing in X-rays, visible light, and radio waves that can persist for tens of thousands of years before dissolving into the surrounding interstellar medium. The most famous remnant is the Crab Nebula, the result of a supernova observed by Chinese astronomers in 1054 AD, still visible today as an expanding cloud about 11 light-years in diameter. The last supernova observed within the Milky Way occurred in 1604, Kepler's supernova, and was visible to the naked eye for more than a year. If a supernova occurred today just a few hundred light-years from the Sun, it would be visible in daylight and would cast shadows at night. The absence of such an event over the past for centuries is statistically normal, but it means that entire generations of humanity have never witnessed one of the most dramatic phenomena the universe produces in the Milky Way. What almost no one realizes is that supernovae play a dual role in the interstellar medium cycle. At the same time they destroy and disperse existing gas clouds, locally inhibiting star formation, they also compress the gas around the shock wave, potentially triggering the collapse of neighboring clouds and stimulating a new generation of stars. Destruction and creation happening simultaneously, in the same event, at different scales. The Milky Way contains roughly 100 to 400 billion stars. That enormous range is not careless imprecision. It's a genuine reflection of the difficulty of counting objects distributed across 100,000 light-years of space, partially obscured by dust, varying enormously in brightness. And the count is done indirectly, combining measurements of the total mass of the galactic disk with estimates of how many stars of each mass are formed on average. The most common stars in the galaxy are red dwarfs, low-mass stars, between 8 and 50% of the Sun's mass, which account for roughly 70 to 75% of all stars in the galaxy. Despite that overwhelming numerical dominance, they're so faint that none are visible to the naked eye. Proxima Centauri, the closest star to the Sun, is only 4.2 light-years away and still requires a telescope to be seen. What red dwarfs lack in brightness, they make up for in longevity. A typical red dwarf has enough fuel to burn for tens to hundreds of billions of years. No red dwarf that has ever existed has reached the end of its life yet. Every single one that formed since the Big Bang is still active. That has an interesting implication for the search for life. Planets around red dwarfs would have billions of additional years to develop complex life compared to planets around stars like the Sun. At the same time, red dwarfs emit ultraviolet flares far more frequently and intensely, which could make their close-in planets hostile, or at least require life to develop very different protective mechanisms from those found on Earth. The Sun is often described as a common, ordinary star. And in terms of mass and temperature, that's reasonably true. But in terms of size, the Sun is above average. About 95% of the Milky Way stars are less massive than the Sun, which means that in practice, it's larger and more luminous than the vast majority of stars in the galaxy. A more luminous than average star warms its planets at greater distances, creating a wider and more distant habitable zone. The Sun also has relatively moderate flare activity compared to red dwarfs, which provides a more stable environment for the evolution of complex life on the surfaces of nearby planets. And with its estimated 10 billion-year lifespan, for 0.6 of which have already been used up, it offers a window of stability long enough for slow evolutionary processes to reach complex outcomes. The question of whether the Sun's mass is a coincidence or a necessity for the kind of life that exists on Earth remains genuinely open. But what's clear is that the combination of the Sun's characteristics, its mass, its stability, its longevity, its position in the galaxy, its position in the thin disk, its position in the local bubble, forms a set of conditions that, together, created an extraordinarily favorable environment for the 4 billion years of biological evolution that took place on the planet orbiting 8 light-minutes away. Binary stars, systems of 2 stars orbiting a common center of mass, are surprisingly common in the Milky Way. It's estimated that between 40 and 70% of solar-type stars exist in binary or multiple systems. Star formation from collapsing gas clouds naturally produces multiple fragments, and the gravitational bond between them is often strong enough to hold them together for billions of years. When one star in a binary system evolves faster and becomes a white dwarf, it can transfer mass from its companion, creating phenomena that wouldn't occur in isolated stars. Classical novae, recurrent novae, and type Ia supernovae, used as standard candles for measuring cosmological distances, all originate in binary systems where a white dwarf accretes mass from its companion until reaching a critical limit and exploding. Cepheids, stars that pulsate with periods between 1 and 100 days, have an extraordinary property that transformed astronomy. There's a direct and well-calibrated relationship between the pulsation period and the star's intrinsic luminosity. Discovered by Henrietta Swan Leavitt in 1908, this period luminosity relationship was the ruler that allowed distances across the universe to be measured precisely enough to demonstrate that the spiral nebulae were independent galaxies, far beyond the limits of the Milky Way. It was Leavitt who gave Hubble the tool that allowed him to expand the known universe beyond the galaxy. Her work was fundamental, and she died in 1921, before receiving any recognition proportional to the importance of what she had discovered. Science has many of those stories. fundamental discoveries made by people whom time was slow to properly recognize. There's something counterintuitive about how we discovered our position in the Milky Way. For centuries, astronomers assumed the Sun was near the center of the galaxy. The Milky Band seemed to distribute itself relatively uniformly around the sky. It wasn't until the early 20th century that this idea was overturned, and the correction came from an unexpected source. The astronomer Harlow Shapley realized, around 1918, that globular clusters weren't distributed uniformly across the sky. There was a clear concentration in the direction of the constellation Sagittarius. If those clusters orbit the center of the galaxy, as he correctly argued, then the center should be in that direction. And if the center was there, the Sun was far from it, about 2/3 of the galactic radius away from the center. It was one of the greatest shifts in perspective in modern astronomy. Earth had already been displaced from the center of the solar system by Copernicus. Now the solar system itself was displaced from the center of the galaxy. The pattern of progressive decentralization repeated itself once more. And it will probably keep repeating, as we come to better understand the structures we're immersed in. The Sun completes one orbit around the center of the Milky Way in approximately 225 to 250 million years. A period called the galactic year. In all of Earth's history, the planet has completed only about 20 of those galactic years. In the time of a single galactic year, civilizations can rise and fall, continents can shift substantially, entire species can evolve or go extinct. The Sun's orbital speed around the galactic center is approximately 220 kilometers per second. A number that doesn't mean much in the abstract. For reference, the speed of sound in air is about 340 meters per second. The Sun moves through space at a speed roughly 650 times greater than the speed of sound. And it carries the entire solar system with it, all the planets, all the moons, all the comets, all the asteroids, the Voyager probe that has been traveling toward interstellar space for decades. All of it moving together, in an orbit around the galactic center, at 220 kilometers per second. And it's completely imperceptible in everyday life. Because everything around us is moving together, in the same direction and at similar speeds, with no external reference to reveal the motion. Beyond that orbital motion, the Sun also gently oscillates up and down relative to the plane of the galactic disk, an oscillation with an amplitude of about 230 light-years above and below the plane and a period of roughly 70 million years. Currently, the Sun is slightly above the average galactic plane, about 56 light-years above it. In approximately 30 million years, it will reach its highest point and begin returning toward the plane, crossing it and repeating the cycle on the other side. That oscillation, so gentle, so slow, so absolutely imperceptible, has been connected in still controversial hypotheses to periodic variations in the rate of comet impacts on Earth. The idea is that when the solar system passes through the galactic plane, gravitational disturbances to the Oort cloud, the reservoir of distant comets at the edge of the solar system, would be amplified, potentially sending more comets into the inner solar system. The correlation with geological mass extinctions is suggestive, but causal evidence is still not conclusive. And it may never be, given the difficulty of distinguishing subtle signals in a geological record that is inevitably incomplete. But the idea itself, that the Earth's movement around the Sun's movement around the galactic center, the Sun's oscillation perpendicular to the galactic disk, and the distribution of mass in the disk could have influenced the history of life on Earth, is one of the most dizzying connections between cosmology and biology that contemporary science has suggested. The Milky Way is not a static backdrop against which life happens. It's a dynamic system that life interacts with. The Gaia satellite, launched in 2013 by the European Space Agency, revolutionized our understanding of the Milky Way in ways that are still being fully absorbed. By measuring the positions, proper motions, and radial velocities of more than 1,800,000,000 stars with unprecedented precision, Gaia transformed the Milky Way from an object to be observed into a dynamic laboratory to be analyzed in unprecedented detail. Among the most notable discoveries from Gaia data is the identification of stellar streams, groups of stars with coherent motions that reveal the history of past mergers and disruptions, and the detection of oscillations in the galactic disk that suggest the Milky Way is still responding to disturbances from billions of years ago. Gaia's data revealed systematic vertical motions in the galactic disk, stars moving up and down in coherent patterns that propagate through the disk like waves. This structure is a consequence of past disruptions that the disk hasn't yet fully absorbed. It's like the surface of a lake still rippling long after a stone has been thrown into it. The Milky Way is a disturbed system, not a structure at rest. And each new dataset reveals additional disturbances that previous generations of instruments lacked the resolution to detect. The Milky Way doesn't exist alone in space. It's accompanied by a collection of smaller galaxies that orbit around it like gravitationally bound satellites. The number of known satellites has grown dramatically over the past 2 decades, from a handful of obvious objects to more than 50 identified systems. And more recent surveys suggest the true number may be much higher, with dozens of ultra-faint dwarf galaxies still awaiting discovery. The satellite galaxies vary enormously in size, mass, and brightness. The Magellanic Clouds are by far the largest and most massive, visible to the naked eye in the southern hemisphere as distinct nebulous patches. At the other extreme are ultra-faint spheroidal dwarf galaxies like Segway 1 and Willman 1. Objects with only a few hundred stars, so diffuse that their surface density is lower than that of the background of distant galaxies. Studying these satellite galaxies is important for reasons that go beyond cataloging. They're the most dark matter-dominated structures known. In some of them, dark matter may account for more than 99% of the total mass. That makes them ideal laboratories for testing dark matter models in extreme regimes. The Large Magellanic Cloud has a mass of about 10 billion solar masses and contains the Tarantula Nebula, the largest and most active star-forming region in the local group of galaxies. A region so rich and dense in star formation that, if it were in the position of the Orion Nebula, it would be visible in daylight and would cast shadows at night. Recent studies suggest that the Magellanic Clouds may be relatively recent visitors to the Milky Way's neighborhood, arriving for the first time within 300,000 light-years of the galactic center only a few billion years ago. If confirmed, that means we're observing the clouds in a transitional phase of their relationship with the Milky Way, before they're eventually absorbed. While they're here, the Magellanic Clouds have a measurable gravitational effect on the galactic disk. The galactic disk shows a gradual ripple, called warping or deformation, that becomes more pronounced in the outer regions. The most likely cause is the gravitational influence of the Magellanic Clouds, whose orbital motion pulls the disk asymmetrically as they orbit the main galaxy. A 2019 study, using data from more than 1,300 pulsating stars, produced the most precise three-dimensional map of this warping ever made. The outer disk may be distorted by up to 20,000 light-years relative to the central plane in the most affected regions. A subtle distortion in proportional terms, but of monumental scale in absolute terms. The local group is the name given to the collection of galaxies to which the Milky Way belongs. More than 50 galaxies distributed across a volume of about 10 million light-years in diameter. And the two are approaching each other. The current approach speed is about 110 kilometers per second. In approximately 4.5 billion years, they'll collide and eventually merge into a single elliptical galaxy. That merger won't destroy the stars. Galaxies are enormously empty structures, and the probability of two stars directly colliding during a galactic merger is virtually zero. What will happen is a complex gravitational dance, where the two galaxies interpenetrate, partially separate, and come back together in multiple passes over billions of years, until the two structures merge into an elliptical galaxy that will no longer have the elegant spiral arms that currently characterize both the Milky Way and Andromeda. Elliptical galaxies are older and less active structures in terms of star formation. It's believed that many of them formed through mergers of spiral galaxies in the universe's past. The current Milky Way is, in a certain sense, a spiral galaxy that hasn't yet found its final merger partner. The Sun may be thrown into a completely different orbit during the merger. The night sky will be transformed into something unrecognizable, with the Andromeda galaxy gradually growing until it dominates the entire visual field. The Milky Way will cease to exist as an independent structure. And life, if it still exists on any planet by then, will likely perceive nothing immediate. The galactic merger takes place on timescales that exceed any biological consciousness by many orders of magnitude. The local group, in turn, is located at the edge of the Virgo supercluster, a much larger structure containing thousands of galaxies. And the Virgo supercluster is just a substructure of an even larger structure called Laniakea, identified in 2014, which contains more than 100,000 galaxies and extends across about 520 million light-years. Laniakea means immeasurable heaven in Hawaiian. The name was chosen by a team of researchers who mapped the flow of galaxy motions around them and